Hi, I'm Yinzhan, and I'm going to talk about hardness for triangle problems on the even more believable hypothesis, reductions from real APSP, real three-sum, and OV. This is joint work with Timothy M. Chen and Virginia Vassilevska Williams. There are three central hypotheses in fine-grained complexity. The three-sum hypothesis states that given a list of n integers that are polynomially bounded, detecting if three of the numbers sum up to 0 requires essentially n squared time. The APSP hypothesis states that computing all pairs shortest passes for an n-node graph with edge weights that are polynomially bounded requires essentially n cubed time. And the strong exponential time hypothesis states that for every positive epsilon, there exists k such that k set on n variables cannot be solved in O 2 to the 1 minus epsilon times n time. And in all these hypotheses, people consider the word-round model of computation with O log n bit words. As we don't know which of these hypotheses actually hold, it's important to consider weaker or more believable hypotheses. Abut, Vassilevska, Williams, and Yu considered the following hypothesis, which states that at least one of the three-sum hypotheses, the APSP hypothesis, O says is true. Even if one or two of the three central hypotheses fails, this hypothesis will still hold. They consider the triangle collection problem, which is defined as follows. We are given an n-node graph with node colors, and we need to determine whether it is true that for each triple of distinct colors ABC, there is a triangle whose nodes have these colors. For example, in this graph, there is no triangle whose node colors are red, yellow, and green. So we output a no for this graph. If we add one extra edge, we can verify that for each triple of distinct colors, there is indeed a triangle with these colors. So output a yes. Abut, Vassilevska, Williams, and Yu showed that under hypothesis 1, triangle collection requires essentially n cubed time. They also showed conditional lower bound under hypothesis 1 for many dynamic problems. Specifically, they show that under hypothesis 1, any fully dynamic algorithm for the counting versions of single source reachability, the counting version of strongly connected components, and the counting version of single source subgraph connectivity or max flow for n-node graphs requires either amortized into the 1 minus little o1 update or query time, or into the 3 minus little o1 preprocessing time. And they achieved this result via reductions from certain version of triangle collection. So triangle collection is not just a made-up problem, it also has applications for dynamic algorithms. The motivating question for our paper is that whether there is a natural hypothesis that is weaker than hypothesis 1 and implies similar hardness results. To this end, we consider an even weaker hypothesis, hypothesis 2, which states that at least one of the real three-sum hypotheses, the real APSP hypothesis, or the OV hypothesis is true. Even though we haven't defined the real three-sum hypothesis or the real APSP hypothesis yet, intuitively, the real versions of these two problems should be harder than the integer versions. So intuitively speaking, the real three-sum hypothesis and the real APSP hypothesis are weaker than the three-sum hypothesis and the APSP hypothesis, respectively. Also, it is well known that Thes implies the OV hypothesis, so the OV hypothesis is weaker than Thes. Now, let's define the real three-sum hypothesis. This hypothesis states that given n real numbers, detecting if three of the numbers sum up to 0 requires essentially n squared time in a reasonable real-round model. we'll come back to the definition of reasonable real-run model later. For integer three-sum, a running time that's roughly n squared over log square n was known since a work by Baran, Demin, and Petrescu. But such a running time for real three-sum is only known after many more works and after more than 10 years. So it seems that it is more difficult to design algorithms for real three-sum. Therefore, real three-sum is potentially harder, and the real three-sum hypothesis is more likely to hold. On the lower bound side, many reductions from integer three-sum actually stop working from real three-sum because often hashing techniques are used, especially since the work by Petrescu. So that means that we need to design new reductions for the real three-sum hypothesis, and we cannot just use existing reductions for our purpose. The real APSP hypothesis states that computing APSP for an n-node graph with real edge weights requires essentially n-cube time in a reasonable real-run model. Again, we'll come back to the definition of the model later. Similar to three-sum, some lower bounds on the integer APSP hypothesis also utilize hashing techniques. So we also need to design new reductions for real APSP hypothesis. Now let's discuss reasonable real-run. The reason we need the notion of reasonable is because unrestricted real-run could be too powerful for the purpose of fine-grained complexity. For instance, if we allow all arithmetic operations between real numbers, the flow function, and the comparisons, then we can actually solve real three-sum in truly subquadratic time and real APSP in truly subcubic time. And therefore, the real three-sum and the real APSP hypothesis are not true in this very strong model. Even if we disallow division and the flow function, we can still solve integer APSP in n to the omega plus little o of 1 time. This does not violate the real APSP hypothesis, but it seems very strong for the purpose of fine-grained complexity. And we also would like to avoid such powerful algorithms. So the meaning of reasonable we consider is the following. The model can be simulated by a word run when the inputs happen to be integers. So in this case, suppose we have an algorithm for a problem with real inputs, then we can transform that algorithm to an algorithm for the integer input case, because we can simulate the algorithm in the real run model with a word run. Therefore, in this case, the integer version of a hypothesis will imply the real version of the hypothesis, and therefore the real version of a hypothesis is indeed weaker than the integer version, as we wanted. Here, I will provide one example of a reasonable real-run model we consider, which we call the real-run model with 4 linear comparisons. It supports all operations supported by a word run, and it can cast integers to rails and sample random integers. It can also compare A plus B with C, or compare A plus B with C plus D, where A, B, C, D are integers, are inputs of a problem. This model suffices for all of our reductions except for real APSP, because for APSP, we at least need to store path lengths in the model. So for APSP, we have to allow some restricted additions in order for the model to be able to store path lengths. But even with that addition, the model will still be reasonable. Here's a figure of our mean reductions. And the goal is to reduce OV, real APSP, and the real three-sum to some versions of triangle collection. For OV and the real APSP, we defined a new problem called colorful BMM as an intermediate problem in the reduction. And we first reduce them to colorful BMM, then reduce to some version of triangle collection. For real APSP and the real three-sum, we first reduce them to the all-edges sparse triangle problem, which itself is a well-studied problem in fine-grained complexity. And then we reduce that problem to some version of triangle collection. And the mean theorem we get is the following. We show that under hypothesis 2, the all-color pairs triangle collection problem, which is a variant of triangle collection, requires n to the 2.25 minus little o of 1 time. And here's a reminder of hypothesis 2, and here's a definition of all-color pairs triangle collection. In this problem, we're given an unknown graph with knot colors, and for each pair of distinct colors AB, we need to determine whether it is true that for all colors C that's not A or B, there is a triangle with colors ABC. Comparing with the theorem by Abud, Vassilevska, Williams, and Yu, the important part of our theorem is that now it's under the weaker hypothesis 2, and it also gives a non-trivial lower bound. We can still use previous reductions from some version of triangle collection to dynamic problems and get non-trivial lower bound for many dynamic problems as well under hypothesis 2 now. Okay, in the rest of this talk, I will focus on the reduction from real APSP to all-edges sparse triangle, because this reduction exemplifies how we deal with real numbers. Let me first define all-edges sparse triangle. In this problem, we are given an M-edge graph, and for each edge, we need to determine whether it is in a triangle. In another version of the problem, we instead need to output such a triangle if for each edge if a triangle exists. But it's known that these two versions of the problem are equivalent. Previously, it is known that this problem requires essentially m to the 4/3 time under the three-sum hypothesis or the APSP hypothesis. Now we show that even under the real APSP hypothesis, this problem still requires essentially m to the 4/3 time, and under the real three-sum hypothesis, this problem requires m to the 6/5 time. Note that this m to the 4/3 lower bound is actually tight if the matrix multiplication exponent is 2. Also, there are previous reductions from all-edges sparse triangle to many other problems, such as dynamic reachability and dynamic shortest passes. So combined with these previous reductions, we get that now these other problems have non-trivial lower bounds under the real three-sum hypothesis or the real APSP hypothesis. Let's also define the mean plus product problem, in which we are given two n by n real matrices A and B, and we need to compute an n by n matrix C such that Cij is the minimal value of Cik plus Bkj, Aik plus Bkj. The integer version of mean plus product is known to be equivalent to the integer version of APSP in the Word-RAM model, and their real versions are equivalent in some reasonable real-RAM models. Now we can forget about APSP and focus on mean plus product. And the goal is to show that if real mean plus product for n by n matrices requires essentially n cubed time, then all-edges sparse triangle for m-edge graphs requires m to the 4/3 minus little o1 time in the real-RAM model with 4 linear comparisons. Now, the first step in our reduction is to reduce real mean plus product to this problem called real mean plus product prime, in which we are given an n by square root n real matrix A, a square root n by n real matrix B, and the n-square indices Kij. And the task is to is for every ij, find an arbitrary k prime ij where ai k prime ij plus b k prime ijj is less than ai kij plus b kijj. And we show in our paper that if real mean plus product requires essentially n cube time, then real mean plus product prime requires essentially n to 2.5 time. But we will skip its proof in this talk. Now, finally, we reduce real mean plus product prime to a larger sparse triangle. And the first step is to sort the following list of own square numbers, which are just the numbers of the form aik prime minus aik or bkj minus bk prime j. And we can indeed sort these numbers in our model because essentially each comparison of two numbers in this list can be handled by for linear comparison. Later, we'll use the rank of these numbers in the sorted order of L to compare these numbers. Let's also define dyadic interval. These are just intervals whose left endpoints have the form 2 to the s times t, and the right endpoints have the form 2 to the s times t plus 1 minus 1 for non-negative integers s and t. Here are all the dyadic intervals between 0 and 15. A nice property of them is that for non-negative integers x and y, we have x less than y if and only if there exists dyadic interval I such that x is in its left half and y is in its right half. Also, it suffices to only consider dyadic intervals completely contained between 0 and O length of L. So we'll reduce each instance of mean plus product prime to multiple instances of larger sparse triangle. So in each stage, we fix some k, that's an integer, less than square root n, and the subset of pairs ij, which we call p, and we allow at most n to the 1.5 pairs inside p. And for every pair inside p, we require that kij is equal to k. Note that even for some values of k, it's possible that the number of ij with kij equals k is larger than n to 1.5, but we can split them into multiple stages. And it's not difficult to see that overall we still have all square root n instances. Now, for each such instance, we create the following tripartite graph, where the left vertices are indexed by I, the right vertices are indexed by j, and the top vertices are indexed by pairs k prime I, where k prime is an integer less than square root n, and I is a dyadic interval. Between I and j, we add an edge if and only if ij is inside P. Between j and k prime I, we add an edge if and only if the rank of bkj minus bk prime j in L is in the right half of I, and recall that we know the rank from a previous step. Similarly, if the rank of aik prime minus aik in L is in the left half of I, we add an edge between I and k prime I. Now let's consider when an edge ij is inside a triangle. By definition, it's in a triangle if and only if there exist k prime and I, such that the rank of aik prime minus aik is in the left half of I, and the rank of bkj minus bk prime j is in the right half of I. And by the property of dyadic intervals, it's equivalent to that there exists k prime such that the rank of aik prime minus aik is less than the rank of bkj minus bk prime j. And simply by definition of rank, it's further equivalent to that there exists k prime such that aik prime minus aik is less than bkj minus bk prime j. And we can replace k with kij because by definition, ij is inside P, so Kij must be equal to K. Finally, it's equivalent to that there exists K prime such that Aik prime plus Bk prime j is less than Ai Kij plus Bkij j, and such a K prime is exactly what the mean plus product prime problem asks for. It's worth noting that the final step is the famous Friedman's trick. Now let's analyze the number of edges. The number of bottom edges is clearly the size of P, which is n to 1.5. And for the number of left edges, we consider each pair of Ik prime. And once we fix I and K prime, the rank of Aik prime minus Aik in L is a fixed integer. And each integer is not hard to see that each integer is in at most O log n dyadic intervals. Therefore, the number of left edges is at most n to 1.5 log n. And similarly, the number of right edges is also at most n to 1.5 log n. So overall, we have at most n to the 1.5, roughly n to 1.5 edges. Now, suppose we can solve each instance of OIJ sparse triangle significantly faster than m to the 4/3, then we can solve each instance faster than n squared. And that means that real mean plus product prime can be solved in much faster than n to the 2.5 time, which will validate the real APSP hypothesis. Okay, and that finishes the proof. Now, in our paper, we also have some results not shown in the figure of mean reductions. And here I will provide some examples. So if we instead consider the counting version of OIJ sparse triangle, in which for each edge in a graph, we need to count the number of triangles it is in, then we show that this problem requires m to the 4/3 minus little o of 1 time under the real 3-sum hypothesis. And this is tight. We also have reductions from a real version of a problem to its integer version. For instance, we show that under the real 3-sum hypothesis, integer of numbers 3-sum for n numbers requires n to the 6/5 minus little o of 1 time. And it will be very interesting to improve this lower bound or even show a tighter lower bound. Thank you.